All right, so we do actually have quite a few objectives for today, and our time is already growing short. Now, I think we already finished outlining the principal mechanisms in the production of electrical power, so we're not going to continue with that one. I think we all did get to manipulate a few of the generators that I had. We do want to identify different world energy sources. We've already been doing that, but we should do that just a little bit. Well, we should do it again. We want to outline and distinguish between renewable and non-renewable energy sources. We want to define the energy density of a fuel. We want to be able to do calculations with energy density, which will help us discuss how the choice of fuel is influenced by its energy density. And then we want to, and I don't know that we'll get to this, state the relative proportions of the world's energy use, right? Of the different energy sources based on how much they're used in the world. All right, so when you look at your own country's energy use, or when we look at the world average eventually, we're going to find that for most countries, and for definitely the world as a whole, the vast majority of the energy is from fossil fuels. So what the heck do we mean when we say fossil fuels? Right? I think we need to make sure we agree on what that means. Justin, what do we mean?
Well, there's like organisms that died and just compressed into these into a constituent carbon.
Yeah. So the fuel is from dead stuff, right? The fuel is derived from dead organisms. Absolutely. So coal, right, is derived from dead organisms. Oil, natural gas. And I am not necessarily always going to use the full term natural gas. If I say gas, I mean natural gas. I do not mean gasoline. I do not mean the stuff that you put in your car, right? We mean natural gas, the stuff that comes out of your stoves if you have gas stoves. Peat, so that came up from, whose was that? Somebody back there had peat? Yeah, Cassie had peat. What country was that? Finland. So peat is dead plant matter that's very old and very compressed, but nowhere near as hard as coal. So I think in Ireland, for some reason I associate peat bogs with Ireland. I don't know why. Maybe I saw a cartoon where a leprechaun lived in peat bogs. But peat bogs would be, it's swampy, very fibrous. If we gave it, a few million years and buried it really deep, it would turn into coal. But we haven't done that yet. All right, so that's sort of what peat is. And then biomass. What would be the most common kind of biomass that people are using for fuel, Cliff? Yeah, wood. Right. How about another one? Nah. Ethanol, right, is derived from, it can be derived from anything. In this country, it's usually derived from corn. That would be biomass as well. All right, so all of this stuff is from once living stuff, so we call it fossil fuels, and that's probably somewhere in the neighborhood of 80% to maybe 85% of how we produce power in the world still today. Now, all of these things, right, all of these fuels, we are ultimately combusting them or burning them in order to heat up water to make steam and then drive a turbine. Did we talk about turbines last time? I think we did. I think we did. Right, like a wind turbine. And when we burn all these things, they do produce carbon dioxide and maybe some other stuff, right? So if we want to do the chemical reaction to this stuff, we'll have our fuel. When we burn something, we are reacting it with oxygen. And then our products would be like CO2, water, right, energy, heat, and maybe other stuff. Depends what else is present in the fuel. All right, why is that significant, in particular this one? Why is that significant? Nick?
That's a greenhouse gas.
It's a greenhouse gas, right. So we're going to work our way through for the next few weeks, probably up until close to spring break, the different ways that we make electricity, not out of just these. Really, these we're just going to focus on next class. We're going to work our way through uranium for a couple of classes, solar, waves, hydroelectric, right, all that stuff. And then move on to the physics behind climate change, right? So we're going to care about this stuff a whole lot a little bit later in the topic. All right, so we want to recognize that most of the world's power comes from fossil fuels, and that is a problem because inherently they produce a greenhouse gas. And they might produce other stuff, especially if you're coal or peat. Natural gas isn't so bad. All right, let me pause for questions there before we make one final point about the fossil fuels. Okay. For all of the fossil fuels, right, that stuff we could trace back to the sun. All right, for coal, for oil, for natural gas. Coal usually came from like plant matter, right? Oil and natural gas usually come from like marine, like phytoplankton, diatoms, like junk like that. Those things are all photosynthetic. Right, so all of these fossil fuels came originally from sunlight, right? And then photosynthesis allowed the sunlight to be, to turn into biomass. So all the fossil fuels came from the sun. Now, most of our other energy sources we can trace back to the sun also. So let's take 90 seconds and see if we can identify the other energy sources besides those 5. And you can cheat and look at your country's energy makeups if you want. So Jeffrey, what's one other one?
Solar.
Solar, absolutely. Tessa, what's another other one? No, yeah, anything that's not one of those or solar. Yeah, anything else. All right, so Tessa her country doesn't have any others. Colin. Hydro. Yeah. I don't know what that means either. I actually think I might know what it means, but I'm not sure. Lauren, what else? Nuclear. Right. Kelly, what else? Not too many others. Yours doesn't have design. Is yours up? You didn't do. Wait, you did do this part.
I have thermal and import.
And who?
Import.
Import. All right. All right. Yeah, Nick.
Geothermal?
Yeah. So I think that the thermal and heat might mean geothermal. That'd be my best guess. There's still a couple others. Elizabeth. Wind. Yeah. Yeah, Justin. Tidal we would actually include with well, tidal we're going to include with hydroelectric because the ways in which we harness it are the same, but for this discussion it's actually different. And then any others? Yeah, Sarah?
Is petroleum the same as...
Petroleum is the same as oil. Yeah, thank you very much for that clarification. Petroleum is the same thing as oil, that's right. Paul, you have another?
No.
All right, anybody else? Yeah.
waste.
Oh, all right. What country was that?
The Netherlands.
Netherlands. All right. So let's make sure real quick we know what each of these are, and then if we can trace them to the sun or not. So solar. So people like get these solar panels on their roofs, right? Because that comes from the sun. No, pretty obvious.
Does it?
Hydroelectric. Can we trace that to the sun? I think so. I think so. Isn't there a cycle?
Oh, yeah.
What's it called?
Watershed.
The hydrologic cycle, right? And what's the step in that comes from the sun? Evaporation, right? We evaporate the water, right? Then it goes and forms clouds and it rains and it goes into the rivers, right? That's the hydro. So we need evaporation, which we can trace to the sun. Nuclear? That's not from the sun. The uranium fuel, that's not formed due to sunlight or in the sun, so that's not from the sun. Geothermal, can we trace that to the sun? I don't think so. Right, geothermal, we dig down about 1,000 feet, 2,000 feet. Stuff's hotter down there, and based on that temperature difference between the surface of the Earth and 2,000 feet deep, we can create electricity just based on that temperature difference. And that heat 2,000 feet down, that's not coming from the sun. Wind, can we trace that to the sun? Yeah, we sure can, right? The sun drives the weather patterns, so for sure. Tidal? No, what did we say before? I think it was number 2 from page 194, moon.
The moon.
Right? Moon.
Doesn't the sun play a part in that?
The sun does pull on stuff, but the high and low tide that sweep past a couple times a day, that's from the moon. That's from the moon. So no, I'm going to say that's not from the sun. Elizabeth?
I agree that the moon is a source of energy, but is it possible to stretch it a bit and say that the sun, which causes the Earth to move around it, which causes
I mean, we could stretch it with uranium and say, well, not in our sun, but in some other sun, there was supernova and formed all the heavier stuff, and we could have anything heavier than carbon form that way. So yeah, let's not stretch it that much. All right, and then, so waste. What is it? Sarah said Netherlands had waste. Justin, what's that mean?
Well, like I think in Norway they do the same thing. They take
We do it too.
They
Go
take
ahead.
the garbage and they just light it up.
Yeah. Anybody work or volunteer at like a hospital? Leia, Lauren? Do you have to collect garbage, or do they have other people that do that? They have other people? Do you know where they bring it?
They always just take it down to like the basement.
Take it down to the basement. That sounds weird, right? Mr. Rick doesn't take our waste to our basement. No.
Do
we have it?
Irrelevant. They take the medical waste to, well, they take definitely medical waste, right? Because that stuff you don't want to truck that stuff around. It's like dangerous. Like we mark it biohazard, right? We incinerate. So every hospital that I know of has an incinerator, which is where that waste goes, and it just burns it at a really high temperature. So if there is virus whatevers or bacteria whatevers, like they'll get destroyed in that high temperature fire. But if we use that to help heat the hospital or do something, then we can include that as an energy source. And we can actually include it as a renewable energy source, which we'll get to in 2 minutes. So usually we think renewable energy means like environmentally friendly. I don't know that burning garbage is typically thought of as environmentally friendly. But yeah, waste would be literally burning garbage, but then using some of that energy for stuff. Rob?
Do the hospitals actually use that energy?
Oh, I think they probably do. At least some of it. I think they probably do. I bet you that they get like extra tax breaks if they do. Because then they're a renewable energy provider, right? And I mean, it saves on their energy bill, but also they probably get some tax credits. All right, so let's morph right into this discussion on renewable versus non-renewable energy sources. There's a sort of clear distinction between renewable and non-renewable. It's not crystal clear though. A non-renewable source is one that I'm saying is depleted when it's used, right? So like we use it up, right? We can't use it again. But maybe a better way to think about it is a renewable source is one that can be replenished as it's used. Right? So it's not a crystal clear distinction, but it's actually as clear as I can get. So coal, can that be replenished as it's used up? No, it takes millions and millions of years for organic matter to form into coal. So no, we can't wait millions and millions of years. No, that's not replenished as it's used up. So coal is a non-renewable source. We're not anywhere close to running out of coal, but we can't replenish it as it's used up. How about wind? Can we replenish the wind as it's used up?
Yeah.
Yeah, the sun keeps creating new weather patterns, and yeah, just because we take energy out of wind, there certainly will be more wind right behind it. So yeah, we are going to call that renewable. How about tidal? Is there going to be more tidal that can be replenished as we use that? Absolutely, as long as the moon stays around. So that's renewable. Solar, we use solar. Does it get replenished? Yeah, there's more sunlight, right? The sun's not going anywhere for a few billion years. Oil, can we replenish that? No, millions and millions of years for that stuff to reform, so non-renewable. Natural gas, same thing as oil. These things form in the exact same way that we'll talk about a little more next class. That's non-renewable. Nuclear,
Maybe.
we can make more uranium-235 as we fission it. Not really. Not really, no. No, nuclear is non-renewable. No, we can't make, I suppose could make uranium-235 if we fuse other stuff together, but unlikely because the heavier stuff likes to do fission to get more stable, and imagine how expensive that would be to do enough artificial transmutations to make some more uranium fuel. Definitely not. Nick?
What if we just kept splitting like the products of fission until they got down to hydrogen, and then we fuse them like a little more?
Yeah, I'm not saying we couldn't do that, but for purposes of renewable, non-renewable, there's no way we could do that like in any sort of timely economic fashion. But better yet, we got to remember this thing, and that this stuff likes to do fission to get more stable, and this stuff likes to do fusion. So I'm not going to say it's impossible to fusion this stuff or to fission this stuff, but it doesn't really work. It doesn't really work out. We probably could do it a little bit with a major energy expenditure, but you can't really do that. Which ones did I miss in this list up here? Hydro. Oh, I didn't get hydroelectric. So hydroelectric, can that be replenished as it's used? Absolutely. Yeah, there's more water right behind it. Absolutely. What else? Geothermal. Yeah, I mean geothermal actually isn't really one that we look at, so I don't really care about it. I suppose we could call it renewable because about half of the energy that led to heating up that stuff 2,000 feet down is from radioactivity, and that keeps happening. The other half is kind of heat that has stuck around since the Earth was formed. That we can't really replenish. So geothermal might be a little bit problematic. If I had to say though, I'd say renewable. I think that pretty much covers it. All right. So other follow-up questions from anybody on classifying these or hydro as renewable or non-renewable? Yeah.
Do we need to classify waste?
We do not need to classify waste, but if we did, I'd probably say renewable because I don't think we're going to run out of waste anytime soon. Well, I think we're going to keep generating waste at a faster rate than we ever would be making energy from it. All right, very good. So our next objective was a defined objective, but it's more than that. So energy density is a quantity that we talk about very frequently when we're looking at our different energy sources. The definition of it is the energy stored in one of our fuels per unit mass. Probably a better definition is the energy that can be released from our fuel per unit mass, but either way it's fine. All right, so energy density would literally be an amount of energy divided by a mass. Now in the non-IB world, they just as commonly talk about energy density as the energy per volume, but we don't. All right, we're just talking about energy per mass. But other places you might see energy per volume. All right, so let's look at the energy density of some of our common ways of producing energy. So we care about this column, right? We do not care about the energy per unit volume. So at the high end of the spectrum, we have our nuclear fuels, all right? So 600 million megajoules per kilogram of fuel, or 88 million megajoules per kilogram of fuel. That is a ridiculous amount of energy. Our fossil fuels are orders and orders and orders of magnitude less than that. All right? Take note also that fusion is an order of magnitude larger than fission. Right? So it would be great if we can overcome these problems with generating electricity by doing fusion. Now, we certainly want to know that the energy density of the nuclear stuff is way more than anything else, but we also want to be able to kind of internally rank our fossil fuels, all right? So CNG, what the heck is that? The heck is that? Cassie? Something natural gas is correct. Now for the something. Here's a big hint. 200 bar. That's a big hint. If you remember 9th grade chemistry.
Yeah, it's pressure.
Bar is a unit of pressure, okay.
Oh, compressed.
Compressed natural gas. Right. So very high pressure natural gas. In fact, it's so high pressure that it's probably in a liquid state. But we still call it natural gas if it's in a liquid state. All right, so natural gas, at least compressed natural gas, is more energy dense than our other fossil fuels, and coal is less energy dense than our other fossil fuels. All right, so we do want to be able to kind of have that internal ranking of natural gas, then oil, then coal. And then hydro is the only other one up here. Right, that's tiny because we're talking about gravitational potential energy is the energy that we're storing in that fuel. So it's very tiny. And that's for a 100-meter dam height. Most dams would be about that. There are some that are quite a bit taller than that, but not like 100 times taller than that. Robin?
So is there a correlation between energy density and efficiency of like using it?
Is there a correlation between energy density and efficiency?
Oh.
For the fossil fuel ones, possibly, but not. For a given type of plant, yes. For a given type of plant, yes. So a natural gas plant and a coal plant are kind of the exact same thing. And natural gas does happen to be quite a bit more efficient than coal. So yeah, as long as we're not comparing like a hydroelectric station to like a thermal power plant, fine. We can make that statement. All right. So what do we want? In addition to being able to define energy density, we want to be able to do calculations if we know the energy density to like find out like how much fuel we need to burn in order to produce the amount of power that we need. So we're going to do a couple of problems where we will do that type of calculation. So power plants, they often like publish how powerful they can be, right? So one of the closer power plants to us is in Mercer County. It's a coal plant. It's called the Mercer Generating Station. And they burn coal and say that they can produce 777 megawatts of power. Right, now that's if they are operating at full power. Like that's as powerful as they could possibly be. So I'd like to do a calculation that's going to be an overestimate where they're operating at full power, right, 100% capacity, for a full 24 hours, right? How much coal would they have to burn through in a single day, right? So I'm going to highly recommend that you do copy down my solution to this so that you're able to look at it as you do other ones on your own. So I'm going to start off by writing down the power of the plant, 777 megawatts. And then the next thing I'm going to do is just acknowledge that a megawatt is the same thing as a megajoule per second. The only other piece of information that I need is the energy density of the fuel. All right, so I'm going to flash back to the previous slide, and I need you to write down the energy density of coal. All right, I'll write it down too. So bituminous coal, bituminous is one type of coal. We'll assume that it's that. So 24 megajoules per kilogram. And that's kind of a lot. 24,000 joules if you have a kilogram of coal. That's kind of, even though it's bad, that's still a lot of energy stored in there. All right, and then all I really need, well, what I want to do next is I want to find the rate at which the coal is burned. Right, the rate at which coal was burned would be measured in like kilograms per second. All right, so I have one quantity that's megajoules per second, another quantity that's megajoules per kilogram. So I ought to be able to somehow combine these two things to end up with kilograms per second. Does this kind of look familiar?
Yeah.
From like the test question with the fusing, right? So what do I need to do? I think I'm going to need to take this one and divide it by this one. Let's see if that works. Let's see if that works. So 777 megajoules per second divided by 24 megajoules per kilogram. That is going to work because the megajoules cancels out, and then the kilograms, which is in the denominator of my denominator, is going to flip up around to the numerator. So let's divide 777 by 24, and that will tell us how many kilograms of coal have to be burned each second. So that I'm getting like 32.375 kilograms per second. So that's about a half, I'm like about 65 kilograms. So that's like 1/2 of me worth of coal every second to produce that 777 megawatts. I'm not done. I still need to find how many kilograms for the whole day, but are there follow-up issues right now about finding that 32 kilograms of coal have to be burned every second? Great. So now I'm just going to use dimensional analysis to turn kilograms per second into kilograms per day. All right? So first, I'm going to go directly from seconds into hours. right? There's 60 seconds in a minute and 60 minutes in an hour. So there are 3,600 seconds in 1 hour. And then there are 24 hours in 1 day. So that will leave me with kilograms per day. Wow. So let's see, 2 significant digits. So I get 2.8 million. Anybody else get that?
Yes.
All right. So almost 3 million kilograms of coal need to be burned each day if they're going to go full power for a full day. So guess what this power plant is like located next to help get that coal down? Well, we
Train
don't-
station.
yeah, probably train tracks, right? Because a train would be, I mean, we need train cars and train cars and train cars. Trucks probably aren't going to cut it. So we either need like super tankers of coal or lots of train cars of coal. And I think it's right next to some train tracks. All right, it's your guys' turn to do one. Another fairly nearby power plant is in Ocean County called the Oyster Creek Nuclear Generating Station. And Oyster Creek, like every other nuclear plant in the United States, fissions uranium-235. And it has a power rating that's not quite as high as the Mercer one, but pretty close, 625 megawatts. So I'd like to do the same calculation, but I'm being silly. For some reason, I want to know just for a half of a day how much they're going to need. So use this as the model for finding that. So why don't you go ahead and write down the 625 megawatts, and then I'll flash back to the previous slide so you can write down the energy density of the uranium. Okay, go ahead. Okay, go for it. If you want to check with your neighbor, check with your neighbor, but go for it. I'd like you to do that.
Well, it makes sense that this is small.
Sorry, was it 8.8 times 10 to the 6th? 10 to the 7th.
Yeah, okay. That's a lot.
If you're getting an answer that's a lot, I think you get it wrong.
Well, no, it's not a lot, like, numerically, it's just a lot, like, when you think about it.
It's like barely in.
That,
I'm getting like 0.31
yeah.
Yeah.
What could units be for that?
kilograms.
Yeah.
Kilograms.
That's, if you think about it.
Right?
that's-
Because the units of time are all canceled out. So all that's left is kilograms. So a third of a kilogram, that would be like, this much uranium, like my dry erase mark. So you can see why, maybe we don't want to burn coal just for transportation purposes, right? Instead of being near a train track, what do we need to be near? Right? Nothing. We need a guy like with something this size, like handcuffed to his wrist, like each day. Right? That's a lot easier than train cars and train cars and train cars and train cars worth of coal. Cliff.
They do. So that's the energy density, right? But they don't actually.
This is the energy density.
Wouldn't they actually use more?
Yes, and I'm going to get to that on the next slide. Nick,
How much does 0.31 kilograms of uranium cost?
what does it cost? Oh man, I mean it's probably pretty expensive. It might even be similar to the cost of